Okay, now we turn our attention to fluid dynamics, meaning fluids in motion. Everything we've looked at up to this point has been fluid statics. Let's start with box number 9. An ideal fluid, meaning an idealized, theoretically perfect fluid, is incompressible and non-viscous. Incompressible means for a given volume of fluid, you can't compress it or expand it. Another way of saying that is a flowing fluid never has any variation in its density. Viscosity basically means resistance to flow. So think of an ideal, theoretically perfect fluid as having no resistance whatsoever to flow. Any teeny tiny bit of force acting on that fluid will cause it to flow. Think of something like honey, though. That honey has a lot of viscosity, which means it's kind of resistant to flowing, and you have to apply a force on it to make it flow. Box number 10, mass flow rate. It basically says what goes in must come out. Because an ideal fluid is incompressible, there's no way it can stretch out or scrunch up as it's flowing through a pipe. Do the dimensional analysis. Mass flow rate is density times the pipe's cross-sectional area times the flowing fluid's velocity. Make sure you end up with kilograms per second. So kilograms per second is a mass flow rate. It's the rate at which mass flows in terms of an ideal flowing fluid. Box number 11, the equation of continuity. This is basically the same as box 10, but it's saying that the mass per second rate flowing through one point in a pipe has to be exactly equal to the mass per second flowing through another region in the same pipe. So for example, if I have 5 kilograms per second of mass flow at the left side of my pipe, I have to have that same 5 kilograms per second mass flow at the right side of my pipe. Here's a pretty good simulation right from Wiley Plus showing the equation of continuity in action. I'm going to keep my eye on a specified volume of fluid as it passes through this pipe. I'm going to loop that a few times, and you can see that that given volume of fluid changes shape and changes velocity as it moves through the pipe, but the rate at which that mass flows never changes. The wide skinny volume you see on the left has a certain amount of mass and a certain amount of volume, and even when it changes shape as it moves through this pipe, both its volume and its mass remain constant. Again, this is because fluids are incompressible. What goes in must come out. Box 11, volume flow rate. This is exactly like mass flow rate, which again was given in box 10 as density times the pipe's cross-sectional area times the fluid's velocity, which evolved into box 11, saying that the rate of mass flow, the kilograms per second number, never changes as an ideal fluid is flowing through a pipe. Look carefully at box 11. If the density of the fluid never changes, let's say you just have some flowing water through a pipe, the density of that water never changes. So on the left side of the equation, rho 1 is going to equal rho 2 on the right side of this equation. So let's divide them out. If we do that, we're left with volume flow rate. Do the dimensional analysis and make sure you can see how volume flow rate is given by cubic meters per second, or the rate of volume flow. Not the rate of mass flow, but the rate of volume flow. Here's the culmination of this entire chapter, the Bernoulli equation. Look at the three terms on the left side. P1 can be thought of as pressure energy density. 1/2 rho V1 squared can be thought of as kinetic energy density, and rho g y1 can be thought of as gravitational potential energy density. You have those three energy entities at one point in the pipe, say for example on the lower left as shown in the drawing. Conservation of energy says if you have all of that energy at the lower left side of the pipe, that same amount of energy has to exist when that given volume of fluid makes it all the way to the top right side of the pipe. Check out this animation. Water flows from a wide, low pipe to a skinny, higher up pipe. I'm going to look at all of the pressure energy density and the kinetic energy density and the gravitational potential energy density that exists with the stream of fluid at the lower left. As it flows from the lower left to the upper right, it speeds up, which means it gains kinetic energy density. It gains height, which means it gains gravitational potential energy density, but it loses pressure energy density. If it didn't lose pressure energy density, then I would be violating the law of conservation of energy. The sum of each of these three energy density terms would be greater on the right side compared to the left side, which is a violation. A key takeaway from Bernoulli is that higher fluid speeds are associated with lower fluid pressures. This profoundly affects a ton of practical applications. The Bernoulli effect explains why baseballs can curve, what gives airplane wings lift, how certain kinds of pumps work, and how air airspeed is determined for airplanes and other aircraft.